Since the dawn of space exploration, mankind has been driven by the desire to explore the cosmos. But before the era of the Space Shuttle, how did we deliver astronauts into space? In the early days, NASA used single-use rockets to send astronauts into space. The Mercury program, which began in 1958, marked America's first human spaceflight initiative. The Mercury Redstone and Mercury Atlas rockets carried astronauts like Alan Shepard and John Glenn, who became the first American to orbit the Earth in 1962. Following Mercury, the Gemini program launched in 1965, using the more powerful Titan II rockets. Gemini missions tested critical spaceflight techniques such as orbital rendezvous, spacewalks, and long-duration flights, all of which were essential for the upcoming Apollo missions. The Apollo program, perhaps the most iconic, utilized the mighty Saturn V rocket. This behemoth carried astronauts to the moon, with the historic Apollo 11 mission in 1969 landing Neil Armstrong and Buzz Aldrin on the lunar surface. However, each of these rockets and capsules were single-use, discarded after their missions, which was costly and resource-intensive. By the 1970s, it became clear that a new approach was necessary. The cost of space exploration was skyrocketing, and the idea of reusing spacecraft became increasingly appealing. NASA envisioned a reusable spaceplane that could launch like a rocket, operate in orbit as a spacecraft, and return to Earth landing like an airplane. This led to the development of the Space Shuttle, a revolutionary concept aimed at making space travel more routine, affordable, and versatile. The design process for the Space Shuttle was one of the most complex engineering challenges ever undertaken. Engineers had to balance conflicting requirements. The shuttle had to be powerful enough to reach orbit, durable enough to withstand the harsh conditions of space, and light enough to glide back to Earth. The shuttle consisted of three main components: the orbiter, the solid rocket boosters, and the external fuel tank. The orbiter, which housed the crew, cargo bay, and the shuttle's main engines, was designed to be reusable for up to 100 missions. The solid rocket boosters, attached to the sides of the external fuel tank, provided the necessary thrust during the initial 2 minutes of flight before being jettisoned and recovered from the ocean for refurbishment and reuse. The external fuel tank, the largest component, carried liquid hydrogen and oxygen to feed the orbiter's main engines during ascent, and was the only part not reused, as it was discarded after each launch. The shuttle's thermal protection system was another critical innovation, comprising thousands of heat-resistant tiles and panels to protect the vehicle during the intense heat of re-entry. This system required meticulous inspection and maintenance after each flight, highlighting the shuttle's intricate and delicate nature. After years of design, development, and rigorous testing, the first Space Shuttle, Columbia, launched on April 12, 1981, marking the beginning of a new era in space exploration. Over the next 30 years, the shuttle fleet expanded to include Challenger, Discovery, Atlantis, and Endeavour. These shuttles completed a total of 135 missions, achieving remarkable milestones, such as the deployment and repair of the Hubble Space Telescope, the assembly and servicing of the International Space Station, and numerous scientific experiments conducted in microgravity. The Space Shuttle program offered numerous benefits to space exploration and science. The shuttle's large cargo bay allowed it to carry significant payloads, including satellites, scientific instruments, and components for the International Space Station. This capability enabled the launch, repair, and maintenance of the Hubble Space Telescope, dramatically enhancing our understanding of the universe. The shuttle also served as a laboratory in space, with its Space Lab module hosting a wide range of scientific experiments. Researchers studied everything from materials science to biology in the microgravity environment, leading to breakthroughs that benefited life on Earth and advanced our knowledge of living and working in space. Furthermore, the shuttle program played a crucial role in international cooperation. The International Space Station, a collaborative effort involving multiple countries, was constructed piece by piece using the shuttle's cargo capabilities. The program also fostered partnerships with other space agencies, paving the way for future collaborative missions. Tragically, the shuttle program was not without its setbacks. On January 28, 1986, the Space Shuttle Challenger disintegrated 73 seconds after launch, resulting in the loss of all 7 crew members, including Krista McAuliffe, a schoolteacher selected to be the first civilian in space. The disaster was caused by the failure of an O-ring seal in its right solid rocket booster, which allowed hot gas to escape and damage the external fuel tank. This led to a catastrophic chain of events that destroyed the shuttle. The Challenger disaster was a profound shock to NASA and the nation. It led to a 32-month hiatus in the shuttle program and a major overhaul of NASA's safety protocols and organizational culture. The Rogers Commission, appointed to investigate the accident, identified both technical flaws and systemic issues within NASA, prompting significant changes to improve safety and management practices. On February 1, 2003, the Space Shuttle Columbia disintegrated upon re-entry into Earth's atmosphere, once again claiming the lives of 7 astronauts. The cause was damage to the orbiter's thermal protection system, which had been compromised by foam insulation shedding from the external fuel tank during launch. A piece of foam struck the left wing, creating a hole that allowed hot gases to penetrate the wing during re-entry, leading to the shuttle's destruction. The Columbia disaster resulted in another suspension of flights and a re-evaluation of the shuttle's safety measures. The Columbia Accident Investigation Board identified critical flaws in both the shuttle's design and NASA's organizational structure. The tragedy underscored the inherent risks of space travel and the need for continuous vigilance and improvement in safety protocols. Despite its achievements, the shuttle program was retired in 2011. The decision was driven by high operational costs, aging technology, and the desire to focus on new exploration goals. The shuttle's complex and maintenance-intensive design made it expensive to operate, and NASA aimed to redirect its resources toward developing new spacecraft capable of deeper space exploration. The final shuttle mission, STS-135, was completed by Atlantis on July 21, 2011, marking the end of an era. The shuttles were subsequently retired and placed in museums across the United States, where they continue to inspire future generations of space enthusiasts and engineers. As we look to the future, new methods of space travel are being developed. Commercial partnerships with companies like SpaceX and Boeing are paving the way for more affordable and reliable access to space. SpaceX's Dragon and Boeing's Starliner capsules have already begun transporting astronauts to the International Space Station, marking a new era of commercial spaceflight. NASA's Artemis program aims to return humans to the moon by the mid-2020s and eventually establish a sustainable presence there. This program will use the Space Launch System, or SLS, a powerful new rocket, and the Orion spacecraft to carry astronauts beyond low Earth orbit. The ultimate goal is to use the moon as a stepping stone for future missions to Mars and beyond. The legacy of the Space Shuttle lives on, inspiring a new generation of space explorers and innovations. The lessons learned from the shuttle program continue to inform current and future space missions, ensuring that humanity's quest to explore the universe remains as strong as ever. The Space Shuttle program was a testament to human ingenuity and perseverance. Its successes and failures have shaped the future of space exploration, reminding us that even in the face of adversity, our quest to explore the universe continues. Thank you for joining us on this journey through the history of the NASA Space Shuttle. Don't forget to like, comment, and subscribe for more fascinating stories about space exploration and beyond.